All right, let's dive into one of those fundamental JavaScript concepts that kind of hides in plain sight. It's something that can trip up developers at all levels, but once you get it, it's like a key that unlocks so much about how to write cleaner, more predictable code. So, where do we start?
We start with this really weird question. Why is an empty array not strictly equal to another empty array in JavaScript? I mean, your gut instinct says this should be true, right? They're both empty arrays. But nope, JavaScript says it's false. And this isn't some quirky bug, it's a core feature. And by the end of this, you'll know exactly why.
You see, the answer to our little puzzle is all about how JavaScript organizes its data. It's not just one big pile of stuff. Think of it more like two completely different worlds, and they each play by their own set of rules. So on one side, you've got your primitive types. These are the basic building blocks, your everyday workhorses. Numbers, strings, booleans, that kind of thing. And on the other side, you've got the non-primitive types. You probably just call these objects. And yeah, that includes arrays and even functions. They're all special kinds of objects under the hood. Now, trying to memorize all the technical differences can be a real headache. So forget that for a second. Let's use a super simple analogy that makes this whole thing crystal clear. Just think of it as the difference between cash in your wallet and a key to a safe deposit box. A primitive type is like cash. Simple. If you have a $5 bill in your hand, you are physically holding the value. That piece of paper is $5. But a non-primitive type, like an array, that's the key. The key itself isn't valuable, right? It just points you to a safe deposit box where all the valuable stuff is actually stored. This difference, being the value versus pointing to the value, is everything. So how does this cache versus key idea actually play out in our code? Well, let's run a little test. Let's see what happens when we try to copy these different data types. This is where the magic and, honestly, a lot of the confusion really starts to happen. Okay, first up, primitives. When you copy a primitive, you're copying the actual value itself. So if wallet A has the number 5, and we say wallet B equals wallet A, JavaScript essentially goes to the bank, gets a brand new, separate 5, and puts it in wallet B. They're completely independent of each other now. But with non-primitives, it's a totally different story. Let's say box X holds a key to a safe deposit box that contains an array with the number 10. If I then say box Y equals box X, I'm not creating a new box. I'm just making a photocopy of the key. That's it. Now box X and box Y both hold keys that unlock the very same box. And this idea of both variables pointing to the same place leads us straight to the next huge difference. What happens when we try to change these values after we've created them? This is all about something called mutability. Let's see how this connects back to our cache and our key. Primitive types are what we call immutable. It's a fancy word, but it just means unchangeable. Think about it. You can't just take a $5 bill and magically turn it into a $10 bill. The value 5 is fixed. It is what it is. If you want 10, you have to get a completely new, different bill. The original 5 is totally unaffected. Non-primitive types, however, are mutable. They can be changed. Because we have the key to the safe deposit box, we can just walk over, unlock it, and change what's inside. We can add more stuff, take things out, whatever we want. The box itself, the object, is being directly altered. So why? Why does JavaScript work this way? Well, it's not random, I promise. It all comes down to how it manages the computer's memory. There are two main places where data gets to live, and this is the real technical reason behind our cache versus key model. Okay, so here's the full story all laid out. Our primitives, our cache, are simple, fixed-size values. They get stored in a super fast, simple part of memory called the stack. Think of it like your wallet for quick and easy access. But our non-primitives are more complex. The object or array itself lives in a big, flexible memory area called the heap. That's our safe deposit box. The variable on the stack just holds the key, which is really just the memory address of that box on the heap. And this is why we compare them differently. Primitives by their actual value, and non-primitives by their reference, or their key. Okay, we've got the theory, we've got the analogy, we've even peeked under the hood at the memory model. With all this knowledge in our back pocket, we can finally go back and solve that initial puzzle once and for all. Let's look at it one last time. We're asking JavaScript, is this empty array strictly equal to this other empty array? Knowing what we know now about keys and boxes, what is JavaScript really comparing here? And there it is. The answer is so clear now. When you write the first empty array,
You're telling JavaScript, hey, go build me a new safe deposit box on the heap and give me the key. Then when you write the second empty array, you're telling it to do the exact same thing again. Go build me another, totally separate safe deposit box and give me the key for that one. So even though both boxes are empty, you're holding two completely different keys.
This quote really hits the nail on the head. The triple equals operator, when it's looking at objects or arrays, does not care what's inside the box. It only cares about one thing. Are the keys identical? Do they point to the exact same spot in memory? And since we created two different arrays, we have two different memory locations, and therefore two different keys, so the comparison has to be false.
So beyond just solving a cool JavaScript brain teaser, why is this so critical for your day-to-day coding? Well, understanding this difference isn't just some academic exercise. It has huge practical implications for the code you write every day. Ever had a bug where you changed an object over here and it mysteriously broke something completely different over there? Yep, this is probably why. You thought you were working with a copy, but you only copied the key, so you were accidentally changing the original data. Getting this concept helps you avoid those nasty side effects, manage application state way more predictably, and just debug those weird issues so much faster. It helps you write code that actually does what you think it's going to do.
So now you know the secret of the key. You're not just passing around values, you're passing around references or directions to where the real value lives. Think about the last time you had some data change when you didn't expect it to. Could this have been the culprit? How is this going to change the way you think about copying an object or an array from now on?